Splash 19, our last keynote. There has been a tradition of having closing keynotes at Splash for the past few years, and I think it's a great tradition. We have wonderful speakers, and our wonderful speaker for today, for our closing keynote, is Frank Dellert, a world-leading vision and robotics researcher. He has been a professor at Georgia Tech since 2001. He got his PhD before that with Sebastian Thrun of autonomous vehicles fame. And Frank has been, like I said, a professor for a while. But he also, in the past few years, made his little adventures in industry. So at first, he was chief scientist of Skydio, a startup company that tried to build the first fully autonomous drone. And I think he will tell us more about that. And then after that, he spent 2 years at Facebook as a technical project lead for something ultra secret that maybe he can, maybe he cannot tell us about, that concerns augmented reality. So, I don't know, between Facebook and fully autonomous drones, maybe our opening keynote was about how computer science can cure all disease. Maybe our closing keynote is about how computer science can lead to our eventual destruction of all humanity. But hopefully Frank has nothing to do with that. And for the past year plus, he returned to his professorial duties. And he's now back to being an academic. And I look forward to hearing about all his interesting work, and especially whatever has to do with languages. Thank you very much for coming, Frank.
All right. Well, thank you for inviting me, and it's great to be here. A little bit intimidating because I'm sort of a programming languages fan, groupie. So you guys are my heroes, making cool new languages. And so throughout, I'll sprinkle some how I changed languages through the course of my career. But this talk is really about robotics, computer vision, and about a graphical language that I came to know across the years. It predated me, but it has made some inroads through my work and others in robotics and vision as a language that people now talk about, sensor fusion. So the outline of my talk is roughly this. I'll give you a little bit of an intro into robotics mainly, because I don't think you're experts. So then I'll talk about factor graphs, which is this graphical language, and some other things. I'll conclude with future directions. All right, so as Yanni said, I actually was a grad student at Carnegie Mellon with Sebastian Thrun. And in 1998, we actually put a robot in the Smithsonian National Museum of American History. And this robot was special in the sense that it had to navigate in the museum, surrounded by people, so it didn't have to, shouldn't bump into people. But also the museum is full of glass cases and stairways that go down, So the robot has to know really, really well, accurately where it is, or it will disappear into a stairwell. And then the experiment is over. And so that was quite important. And note that this robot is equipped with these black holes. They're sonars. So back in '98, sonars were still an often used sensor for robotics. And so the robot localization problem is, given these sonar readings, where am I? Okay, and in '99, so we developed this in '98, but in '99 we published this work on something called Monte Carlo localization. It is, here we use samples to represent the probability distribution over the location of the robot. So this is probabilities as knowledge, right? So in this case, the robot thinks it's either here or here. So the nice thing about samples is that it supports multimodal probability densities to encode the knowledge over a particular space, in this case the location of the robot. And given a bunch of readings over time, eventually it is able to disambiguate where it is in this known map. So this is localization because it's a known map, and the robot tries to localize, that's it, right? Now, one of the success stories of robotics is, believe it or not, vacuum robots. Okay, so many of you might have a robot, and some of you that have a lot of money might have one that maps, okay? Because the ones that do mapping are typically more expensive. And then you can look at, you know, this robot builds a map of your house to sort of systematically clean, you know, your house. And this doesn't use a sonar, it actually uses what is called a LiDAR, which is a laser that scans and gives you distances to objects. And so from, again, integrating over time, you can build a map of the house, of your house, and it builds a map of your house, right? And typically it assumes that, you know, obstacles are static, etc. Sometimes it remaps something. And a student, you know, that was also in the lab back then in Carnegie Mellon sort of applied this sampling-based idea to building maps. So in this case, this is an algorithm called FastSlam, where we use a particle filter, so that's using samples for representing probability distributions. But now the probability distribution is over full trajectories of where the robot was, and each trajectory has associated with it a map. Okay, and so then we're basically doing localization and mapping at the same time. Okay, so that's 2002. The lasers here are planar, right? So they only give you a 2D slice of the environment. Nowadays, if you think about autonomous driving, you know, they have lasers that are full 360, and they have maybe 64 of them. So you get sort of a 3D picture of the environment around you. And this is a marketing video from Velodyne, which is one of the leading LiDAR vendors for autonomous vehicles. And you can see how you know, first of all, the bandwidth of this sensor is just tremendous, right? So you get millions of 3D points per second of the environment around you. You can see obstacles. You can also see shadows that are cast by obstacles, right? So you do have to reason again over time to build a map of this, or to figure out where the cars are and what are cars and what are pedestrians and what are bicyclists. And so this is fueling partly the revolution in autonomous vehicles. And it's quite difficult to do this, and it's probably the most difficult problem in autonomous vehicles is to reliably process these clouds. By the way, Tesla does not have one of these. It has a bunch of cameras looking in all directions. So they're hoping that they can distinguish between pedestrians and bicyclists and cars, etc., just using computer vision alone. Okay. You know, so here is an example of how you can build maps if you have lasers like this. This is work by Ryan Eustace at the University of Michigan, and they took one of these Velodynes, drove it around the campus of the University of Michigan, and built this enormous map of the campus. But autonomous driving companies like Waymo and Uber are building maps of entire cities using this technology. You don't need a laser, though, to build a model of the world. In fact, all of you have probably, you know, I hope that you went up to the Parthenon and took lots of pictures. And all these pictures, some of them make them their way on the web. So you can actually do a Google search. Here there is a Google image search for a city called Dubrovnik. And wouldn't it be amazing if you could just create a model of the world simply from these pictures? And in fact, that is possible. So no lasers involved, just the pictures that you post on Instagram or Facebook or the web. This was back in the day when Flickr was still something, and DSLR still was a word. And so what you can do is build a 3D model of the entire city from a single Google search. Okay, so this is 3.5 million 3D points, all features in Dubrovnik, taken from about 5,000 images, and you could see exactly where the cameras are as well. So you solve a large optimization problem here, an inference problem in computer vision, to figure out what is the 3D model of the city and where were all the cameras when these images were taken. Okay, so you can see that there is large concentrations where all tourists take pictures. Right. This now, you know, Google and Microsoft do amazing things like this, city scale, world scale. But I still think that this video, which is due to Samir Agarwal and Noah Snavely and Steve Zeitz, they're all at the University of Washington. This is one of the most amazing sort of movies out there to show the principle. Okay, so that's from images at a, and you assume that the world doesn't change. With one of my students, I also looked at what if you have images over time, okay? The Acropolis, was there for 2,500 years, and so most of the records we have are paintings. But in the city of Atlanta, actually where Georgia Tech is, was burned to the ground by General Sherman in the Civil War, the U.S. Civil War. So it basically started from zero, and it was right at the start of photography. So we have pictures of when Atlanta was burned down, and then all the way to when it became at this moment, 5 million people metropolis. And so with Grant here, was able to do a 3D reconstruction of Atlanta. Not just 3D reconstruction, but also time. So now we have a little slider here that we can go back and forth in time and see what Atlanta looked like at any given moment. Okay? And so that's cool, and it was funded by National Science Foundation because it allows you to build models of artifacts over time. It is also useful in a different context. My daughter is doing biology at the University of Chicago, and she always asks, "Dad, what are you doing to save the world?" Okay, and we make a tiny contribution, and the tiny contribution is if we can take images of crops over time. So, for example, we take images from this tractor with a camera, and we do this week after week after week. We can build 3D reconstructions using the sort of similar technology to make movies and visualizations like this, where we, in this case, this is broccoli, where we see how the broccoli is growing over time, right? And that allows then, this is technology, so a possible use of this technology is to enable precision agriculture, so that you can see this is where the crop is growing, this is where it's not so growing so well, so you can look at, with machine learning, maybe you can get at the possible causes, and then do precision application of pesticides or other cures for stunted growth. And that actually worked quite well. We were able to figure out where there was compacted soil before, just from the 3D reconstruction itself. And so I do have a vision where in the future there will be many, many drones flying over the fields that are continuously monitoring crops and giving real-time feedback to farmers so that we can sort of be more economical with things like pesticides. Cool. So all of these, I'm hoping that by giving this intro, that I've given you sort of a whirlwind of different applications in robotics and problems in robotics that have to be solved using sensor data, be it sonar or laser or images over time, or a combination of these. We have to do sensor fusion. We have to put everything in a common framework, in a common model, all right? And over 10 years, my students and I have figured out that factor graphs, which is a particular graphical model, are an amazing way to think about these problems, and all of these problems, in fact. And so I'll give you a brief intro to factor graphs, and because you're mostly computer scientists, I'm going to introduce factor graphs using your favorite computer science problem, which is graph coloring. Okay. Graph coloring, of course, okay, so just a little language thing. All of my work at Carnegie Mellon was done with MATLAB, which I've come to hate with a vengeance. And so I took a course by Bob Harper. Bob Harper, of course, is one of the sort of people behind standard ML. And he sort of changed my life by introducing something that I didn't think was possible, but was type inference. And type inference allowed me to sort of be strongly typed, so get away from MATLAB weak typing, be strongly typed without having to write types. And I still type with 2 fingers, so I really hate writing types. Now, what is type inference? Well, it's a constraint satisfaction problem, just like graph coloring. Okay? So graph coloring here, in this context is, well, you have to give a color to each of the provinces of this country, which many of you probably will know. This is which country? Canada, yep. I did a similar talk at Tsinghua in Beijing, and they said, North America? Yeah. But it is Canada, and so these are provinces. And so you have these different colors, and so for example, Quebec and Ontario are here, and so you have to assign a color to Ontario and Quebec, and this little factor here says that they should not be the same color. Oh, and by the way, Quebec, Quebecois, I don't know whether there are any in the room, but Quebecois are very opinionated people, and so they might actually prefer one color over another, maybe blue because it's in their flag, and so that's a unary factor here. So this graph consists of variables, factors, and the whole thing is a factor graph. And this is quite well known as a graphical representation in constraint satisfaction, actually. Cool. So that's both constraint satisfaction can be represented like this, but also if we add preferences like Quebec, it becomes a constraint optimization problem, which is a significantly harder problem. Linear systems are easier. So you all know linear systems from grade school. So this is a system of linear equations, right? Three equations in three variables. Well, the factor graph associated with this is, well, you have three variables, x, y, and z, and each of these equations is a factor that connects two of these variables. But you could have one equation that relates all three, or you can have an equation that only relates one. So you can have unary, binary, or ternary factors here. By the way, there is also a matrix representation now, because this system of linear equations can be represented as a matrix. All right, cool. So it does constraint satisfaction, and hence also, by the way, satisfiability. It does constraint optimization. It does linear equations. It also does sensor fusion. So robot localization, we can say represent the location of the robot over time as these variables that we want to estimate. Now the factors represent knowledge from a sensor. It's approximate knowledge, so maybe there's a probability density involved there, saying, like GPS. GPS is something approximate, and if you're in the city, it's very approximate, okay? But we also have information from, as the robot drives, it has wheel encoders, so it tells us, well, I drove maybe a meter between x1 and x2, so that's also a factor, right? And then finally, if you want to estimate both the location of the robot, so here's a little animation of this is actually a truck driving in a park in Sydney, and it sees a bunch of trees, and so the problem, which is a famous problem in robotics now, called simultaneous localization and mapping, or SLAM, you want to find out where the robot was and where all the trees were in that park. And so the graph associated with this problem is the following. So this is a factor graph that is now the embodiment of a SLAM problem. Okay? So if you take away one thing from this talk, is that factor graphs as a visualization of a large sensor fusion problem or optimization problem here are quite powerful, because just from looking at this graph, you actually see a lot of things. You see that you have this Markov chain, which is the trajectory of the robot. You have relatively few landmarks. Some landmarks will be highly constrained because you have lots of measurements associated with it. Some landmarks, like this one, 22 down there, only has a single measurement associated, so that's probably not going to be very well determined. So just looking at the graph already gives you important information about the problem that you're trying to solve. And at the company that I was at, Skydio, which I will talk about in a minute, factor graphs were on the whiteboard all the time. Okay, so it's a language. I'm arguing that it is a language that you can put on a whiteboard and talk and reason and invent new algorithms simply by having these graphs around. Okay. In this case, all these variables are multivariate. So this is the 2D location of a tree. This is maybe a manifold variable like SC2. What is the XY position and the angle of the truck, or maybe even 6 degree of freedom location of the truck. And typically they are derived from probability densities associated with measurements. So that's SLAM. And then lastly, So computer vision. So here's a 3D point cloud from Chicago, actually. These are all images taken by one of my students, Grant. The movie was made by Young Dian. And the factor graph for the structure from motion problem just looks like the visibility graph. Is a particular point in 3D visible from a particular camera, right? You can also have factors associated with how fast Grant can walk before, or what is the typical interval by which he takes pictures. So you can add sort of factors galore. All right, so I'm hoping, I hope to convince you that sort of factor graphs are fairly universal things that model a variety of different problems. And I've not even touched on all of them, okay? I've looked at polynomial equations are important, and there's a whole field of polynomial equations that is sort of related to this as well. Cool, so that's a representation, but then how do we reason, how do we do inference with these? So this is going to be the most technical part of the talk. I don't have this very prepared speech. I want to teach you something about one of the most amazing algorithms out there, okay, which is the elimination algorithm, which you all know from grade school for solving sort of linear equations. But I'll also teach you sort of how to do sensor fusion with it. And to do that, so why don't I give a small example? And the small example is a small SLAM problem. So you have a robot that takes 3 steps in the world. I've already explained that these factors here are associated with, say, real odometry. These 2 landmarks here might be trees associated with, that the robot sees. And so this tree is seen twice, and this tree is seen once. And for people that like sparse linear algebra, I don't know whether Professor Edelman is still in the audience. So he told me in his talk that he liked matrices. Part of my program is sort of to get people sort of out of the matrix gutter into graphical language land, because I believe that graphs are actually much more powerful and much more general than matrices that they represent. Not that matrices and vectors are not useful in context. So here's a sparse block matrix that is associated with this graph, and the variables actually correspond to columns, and the factors correspond to rows. So if you take a look at this graph and you look at that matrix, you can actually figure out that each of these rows is associated with a particular factor. Now, the elimination algorithm, to solve linear equations, you sort of order your equations and you solve one variable at a time, and then you back substitute. And so for sensor fusion, it's exactly the same story. So we will eliminate, say, L1 first. So we choose an ordering, and then we look at the Markov blanket of L1. We say, what is associated with L1? What determines the fate of the location of this tree? Well, it's seen from position 1 and position 2. So this is the Markov blanket associated with that tree. That creates a small local joint probability density. And any probability density, which represents knowledge in this case, can be factored using something called a chain rule into a conditional density and a smaller joint. And so we eliminate L1 by reformulating it as now a conditional density given on its parents, which separate the rest of the graph from this landmark. This is very powerful, because now the statement that we made is, suppose that I know x1 and x2, then I already know what L1 is. So we eliminated L1 from our consideration, and you can see how the algorithm will continue, right? The algorithm will continue by doing this, eliminating one variable at a time until there's no variables left, okay? And what happens to the matrix, in fact, is that the matrix becomes from rectangular to upper triangular. So I've sort of, those people that know sparse linear algebra can recognize this as a matrix factorization algorithm. But I've actually, the algorithm is completely general. Like the first constraint satisfaction, like satisfiability algorithm by Davis and Putnam was in fact exactly the elimination algorithm, which is quite amazing, right? And you can use it to do constraint satisfaction, constraint optimization, and in this case sensor fusion, or it's solve linear systems. If you apply that to a sort of a non-trivial robotics problem, so here's an example of the whole sequence in the park, which was 4 kilometers of this truck driving around in a park in Sydney, which is by today's standard actually a fairly small problem. But we still have quite a bit of variables, in this case 21,000. And then when we create the factor rev and factor it, here I've shown actually the upper triangular matrix associated with that problem. So we use sparse linear algebra to solve these SLAM problems. And I'm going to say one more technical thing about this, which is very, very important, which is the optimal ordering in the elimination algorithm is in fact unknown, or it's known, but it takes I guess more than polynomial time to get it. People use heuristics to order the columns of those matrices to eliminate the variables. So the order in which you eliminate variables is very important, and even simple heuristics can help reduce the number of computation quite a bit. For example, never separate the x, y, and z associated with a landmark. Okay, that turns out to go from 250,000 to 120,000 non-zeros in the solution. Okay. But these matrices are not graphs, and I told you I want to take you sort of out of the matrix gutter, so I really pushed the student very hard, and I had to push him quite hard. Michael is now actually faculty at Carnegie Mellon, so closing the loop here in a different way. But with Michael, we figured out that the upper triangular matrix R, in fact, has a tree structure. And this tree structure is actually quite well known in machine learning already, which is called we call it the Bayes tree, but it's called the junction tree in machine learning. The junction tree is undirected. In our case, it's a directed junction tree, which is called the Bayes tree. Progressively less people will know the word junction tree because machine learning is now completely dominated by deep learning. And it seems that we're losing an entire generation of people to deep learning scripting. But it will come back. It will come back. The nice thing is that once you know that the solution of your SLAM problem is tree structured, you can use this to do incremental inference and only edit this Bayes tree with new information. And typically, if you order your variables correct, just right, you only do editing operations at the top of this tree. And I have a movie to illustrate this. So this is a movie from 2012 where we have a synthetic mapping example. And this is literally just a dump of the internals of our code, which now I will tell you what this code was written in. Most of this code by Michael and my first batch of students was all written in ML, because Bob Harper converted me to functional programming and type inference. And so the first 7 years, as an assistant professor, I think we wrote over 100,000 lines of OCaml. And then I got tenure. So OCaml, got my tenure, so that's really great. Functional programming rules. But I did find out one thing, which is interesting for a community like yours, right? Which is, I was talking to new students, and there was one really great student that went on to have a stellar career at Google, and he's quite rich now, and he didn't want to work with me. I mean, he wanted to work with me, but he didn't want to learn ML. And so here was an instance I found out, via, that I lost good students because there was a learning curve associated with the language in which we were doing our work, right? And another problem with ML as a language is that we open sourced some of this code and nobody cared. Nobody in robotics cared because Everybody in robotics was working with C++, and so here you have an open source ML library, and it was just downloaded by nobody. Okay, so I switched my entire group. Don't be horrified, to C++, and I tried to imbue sort of functional programming style on it. But of course, if you have 10 people in a group, or and you have 20 or 30 people over time, invariably some people will inject horrible code into C++. But we built this C++ library, gtsm.org, and that one has a lot of traction. So a lot of this factor graph stuff is now you can download it from gtsm.org. It's on GitHub. You can contribute to it. It's BSD licensed. We do have Python and MATLAB wrappers. It has some award-winning stuff in it, which I'm not even going to talk about. It's all based on factor graphs and optimization on manifolds and Lie groups, which are mathematical constructs that you need when you have to think about drones or underwater. It's no longer vectors and vector spaces. We're talking about manifolds like rotation manifolds, etc. And it has reverse automatic differentiation, i.e. backpropagation, built in so it has a little mini language called the expression language that does automatic differentiation on functions that you can create, which is something that we also used quite a bit at Skydio. So with a new crop of students, we worked on this library and did things like very fast structure from motion, by thinking about how to cut up graphs recursively. Kai is now leading an autonomous driving company in China, which is called Holomatic. And in fact, he worked for me then, but I'm working for him now because I am consulting. In the United States, we have this amazing boondoggle that faculty can consult 1 day a week without no questions asked. I mean, you have to do a conflict of interest form, etc. But I now work for Kai 1 day a week, so it's very cool. It's another loop closure. With Alex, we talked about dividing up graphs that are, you can think of if you have multiple drones as a large inference problem with a very large factor graph, but it exists on multiple platforms. So how can you do computation locally on these platforms and cut it up? And then Michael went on and did collaborations with again, Ryan Eustace here, to do things like underwater mapping of the hull of an aircraft carrier. And so this is running ISAM, which is the incremental smoothing and mapping algorithm that I talked about earlier that uses that Bayes tree construct. Something very cool about this robot is it's quite difficult to know where you are or recognize that you've been someplace before underwater. So once in a while, this robot goes up, sticks a little periscope out, looks at the hull, and figures out that it was there just from the image from the periscope. So really cool stuff. And then I don't have pictures of this, but ISAM, Michael's implementation of ISAM ran on the International Space Station on an experiment called the Spheres, that are basically little jet-powered robots on the space station. So this work was all somewhere between 2005 and 2012, 13, and then I took a sabbatical. And so the sabbatical, I was 1 year in Leuven in Belgium, and then which is where I'm from originally. So there was another loop closure back to Leuven. But then this company Skydio called me, and we had a Skype conversation, and they wanted me to be an advisor to their company. And in fact, the person who called me was Adam Bree, who is the CEO. And there were three guys, really, Adam, Abe, and Matt, all MIT grads. Adam and Abe had worked with a friend of mine at Project Wing in Google, and Matt was at a gaming company. He's the CEO, the CTO, and the CXO. Matt is the CXO. Do you know what that stands for? It's the Chief Experience Officer. Okay, so he thinks about the experience of interfacing with the drone. So the company is a drone company, and I decided to join as chief scientist. And the thing that convinced me is this movie. This is a movie that Adam showed me in this very first Skype conversation, and it is actually a fixed-wing aircraft flying in a parking garage. Okay, so that takes quite some technical expertise and stamina, and just sheer don't give up when it breaks, because these things are very flimsy. But Adam was not only an MIT student with Nick at CSAIL, but he was also an avid model plane flyer. So when it breaks, he just replaces the wing. He doesn't give up. Okay. So together we built a drone, and here is the drone. This is like an X-ray of the drone, and it looks like a fairly normal drone. It has shrouded propellers, so 4 of them. It has a nice pan-tilt camera, because the goal of the drone is to film you while you do cool stuff. So it's targeted to rich people that can afford. This was a $2,500 drone, right? But that's the thing in Silicon Valley. There's plenty of rich people that can afford a $2,500 drone, and they go, bike in the hills of Palo Alto and Los Altos, and so they're being filmed. And so that was was our Tesla Model S. Before the masses, this was our expensive entry into the market. So there is a NVIDIA board here with a couple of ARM cores and lots of GPU cores. And there's a big battery that you can hot swap out. But the secret weapon of this drone is not as visible, but it is on this slide. Okay? The secret weapon are these small indentations here, okay, which are barely visible, but they constitute 12 navigation cameras that are distributed around the viewing sphere. So we get full 360 visibility on the environment, and we build a 3D model of the environment using GTSAM and all these things on the fly. So that allows this drone to avoid obstacles while it's following you. Okay, and that's important because we don't want you to sort of drive around on a parking lot. We want you to drive around in a forest. We want you to ski where there is trees. We want you to be completely unconstrained, right? And so let me show you a little bit of the internals. This is a very old video from when I was still at the company. I was there for a year and a half. So this is when we had 6 cameras arranged in 3 stereo pairs. So what we do, they're all sort of low resolution black and white cameras, but we find features, we track those features. From the motion of these features over time, we can actually deduce the trajectory of the drone. And the fact that we have full 360 vision makes this much, much easier, or observable is a technical word. So this is a visualization that I made when I was there. This is the drone. We do this in a little sliding window, and so we get a sparse point cloud around the drone, and we know exactly where the drone is flying. Okay. I'm skipping this slide, but based on that information, which we think of the geometry as sort of like a train track on which we can build other things. Like in this case, we build a 3D model of the world that allows us to do. First of all, we track the person, and then the 3D model allows us to, avoid the trees, etc. Now, this was a story I told until about 2 weeks ago. 2 weeks ago, the second product of Skydio came out. Okay, and instead of 12 navigation cameras, the Skydio 2, which is now only $995. The previous speaker was selling his book, and I'm selling my drone. Okay, so I still have a tiny part in the company. But if you do mountain biking or something like that, or skiing, consider this amazing drone. Okay. It only has 6 navigation cameras, and the 6 are here, arranged in a triangular configuration. And each one of them is a 4K camera, which is a very high resolution camera. And it has a 200 degree, i.e. more than a 180, full viewing sphere field of view. Okay? And that replaces 6 of the 12 cameras from before. And then there is an identical 3-camera rig on the bottom. Okay. Okay, so now I'm going to show you a movie with sound. I hope it's not too loud. That shows, it's a marketing movie, but look out for where you see the 3D model of the world and what it can do. Because this, I do believe that this is the most advanced autonomous system in the world. Okay, this is more advanced than autonomous driving vehicles, etc. So this is not our drone. That's a 3D model that's building. So you just, on the phone, you just say who you want to track, and then from that moment on, it tracks that person. You should also look at the caption. It switches from flying itself, no pilot, which is true. This is not a marketing, it's a marketing movie, but there is no trickery here. This is true footage from the drone. This is a GPS beacon, so now when you take that, you can actually point. So this is something from the Chief Experience software. You just point where you want the drone, and then you release it, and then it follows you from there. And this allows you to sort of do non-line of sight tracking as well, because the drone knows you approximately where you are from GPS. Now this might not be completely legal to go 1.5 kilometers, no line of sight. Okay, so it depends on which country you're in. Okay. This is really great because you can fly the drone like, if you can use a remote control, but the drone will not fly into obstacles. So even if you're a bad pilot, you just tell it where to go, and it will avoid the obstacles, on its own. Right? Which is quite amazing, right? Because that's where most accidents happen. You get your drone, you try to navigate it, and within 10 minutes you've crashed it. Okay, so this is, I think, enough of the... they went all out. They went all out. So this is our attempt at dethroning the most powerful sort of company in this space. This is called DJI, which is a Chinese company, really, really great company. And they managed to make very advanced drones for very little money, actually. And so they're quite a formidable competition. But this drone is made completely in the United States. It's assembled in Redwood City. So it's a little bit more expensive, but we also believe it's much more advanced than anything that DJI can leverage. So anyway, this is what factor graphs can do for you. Okay, so it's because factor graphs are a big part of this product. All right, so I will conclude with some future directions. So first of all, again, so now we're in C++. There's lots of mallocs, and I work with a lot of autonomous something or other companies. And one of the biggest issues is malloc. Okay, malloc is not very certifiable. Malloc can fail. So one need that we see is to create a small, fast, embedded version of GDSAM that can be certified and can run on autonomous vehicles, say, right? And so there's a large market for that. So we're creating an OpenSAM foundation, which we will, in 2 weeks in Macau, we will present to the robotics audience. And the idea is that we find industry members and fund the development of both GTSAM and OpenSAM, which is this new embedded version. And so that's going to be a lot of C, unfortunately, because the certifying agencies are very, very conservative. And if your life depends on it, you want them to be, right? But another thing that I personally would like to explore is code generation and certifiable code generation. Like there's these really cool libraries out there, or programs called, one is Halides, which generates really fast code customized to your memory architecture, and Opt does the same for optimization. So they target different memory architecture, different mix of GPU, CPU. So I think code generation, more than actually building by hand a small certified library, code generation I think is a more robust future. And then finally, in terms of languages, I really liked Professor Edelman's talk about Julia. But I believe Swift is a language that has a lot of the same advantages, and it is very popular. It's very popular with iOS and Mac developers, and it is now Chris Lattner, the creator of Swift, moved to Google, so there's a lot of stuff happening at Google with Swift now, including building differentiable functions, which is the bread and butter of numerical optimization. Deep learning as well, but also GTSAM is built around differentiation, okay? So if we have a language where differentiable functions are first-class citizens, that would be quite an advance, okay? So now I'm working with a very smart student on thinking about manifolds and differentiable manifolds in Swift. So we're sort of talking to the people at Google. One thing that I've started doing is not only looking at the world, but also doing motion planning. So a lot of what Skydio does is trajectory optimization. Where was the robot given a lot of measurement information? Well, if you think about planning of motions, for example, if you want to grab this bottle with this manipulator here, and I want to move it from here to here, that is a motion planning problem. And you can do this with trajectory optimization as well. So why not do that with GTSAM as well? So we've been doing that. In fact, one of the first papers we wrote used all of the machinery that we built for SLAM and Inference to make a very, very fast trajectory optimizer. And that immediately won like a best paper award in robotics, in best journal paper of the year award, in fact. Because we built it on Michael's sort of advances on figuring out the tree structured, the tree structure of the Cholesky factor. We can combine these two things, so we can combine trajectory estimation and planning, because a robot never does what you want, really. Okay, so I'll show a little clip here of this is a robot at Georgia Tech, and as you can see, it's on a base that has omnidirectional wheels, which are these magical things that you can make a robot move in any direction. All right. But omnidirectional wheels on carpet are also very stochastic. They never really do what you think they're going to do. So we constantly, using sensor measurements, adjust knowledge about where the robot was and use that to influence the future plan. And we do this in a very fast incremental estimation and planning loop, all using the same machinery, all using GTSAM. Something that I'm also quite interested in is, actually, this goes back, every time to Professor Edelman's talk about Julia yesterday. His advisor was Nick Trefethen, who was the true first paying customer of MATLAB, okay? And Nick Trefethen has written a book about Chebyshev polynomials and a library called ChepFun, where you can represent functions using Chebyshev polynomials, which are really, really cool things related in a deep sense to the Fourier basis. And I sort of fell in love with Chebyshev polynomials, so I'm just looking for excuses to use Chebyshev polynomials somewhere. And it turns out that there's a field of optimal control called pseudo-spectral optimal control that just does that. So we've used it in one project so far, which is robot calligraphy. So input is a Unicode of a character, a Chinese character, and our robot will then do an internal simulation using Chebyshev polynomials, create an open loop control trajectory for the arm, and then try to write the character that we give it. And so I've been told by, I don't know how to write Chinese characters myself, but a friend of mine from Taiwan told me we can now write at the level of an 8-year-old. So some progress to be made, but I'm sure that with maybe closing the loop and putting vision in the loop, we can get better. And then finally, with my student Mandy, we are doing dynamics. So this is a Puma robot, and so you can plan motions with a robot kinematically. But if you want to do non-trivial things with heavy objects or heavy robots, like if suppose this model was very, very heavy, I might have to sort of swing back and forth a couple of times to put it on the table. And that is inherently dynamic. And so we looked at how factor graphs can encode, because it's just a sparse system of linear equations, the dynamics associated with multi-link manipulators and even parallel robots. And here's a little movie that Mandy made, which is, this is a heavy block, and this is a robot with joint and torque limits. So it cannot lift this object in one go to the top because it doesn't have the torque capability, right? So what it does, it first brings the heavy object closer to the object to minimize the arm to then lift upwards. And that is something that you can only reason about, right, if you know about dynamics. So this is unpublished. We just sort of submitted our first paper, but I'm very excited about this direction as well. So in conclusion, factor graphs are, to me, an amazing language for robotics and computer vision. They span sort of problems from discrete problems like Sudokus and satisfiability to graph coloring to SLAM, to in fact motion planning and robot dynamics. So it's a very versatile language that we've used successfully in a commercial product as well. And I can tell you, there's many companies that are currently using GTSAM and are sort of brought into the factor graph universe through that mechanism. And some I know about, and some I don't know about it, because that's the thing with a BSD licensed library. They don't have to tell you, okay. But we do get a lot of sort of anonymous, hey, how do you do this, and how do you do that on GitHub, So that's also the downside of creating an open source library. Now you have to sort of maintain it, and other people are making money off of it, which is another reason to create this nonprofit foundation. I want to thank all these students whose work I discussed, but also sponsors, National Science Foundation, DARPA sponsored a lot of the development of the C++ version of GTSAM, Army Research Labs, and then gifts from a number of companies. And then I guess I'll take questions here.
So people can just kind of line up here.
Please line up in the middle. I have two microphones. So we can have two I'll start, warm everyone up. Could you show us the GTSAM slide with the C++ code? If we can go over the code a little so we can kind of understand.
If you're going to criticize this is my nightmare, being criticized for my code at a programming languages conference. Thank you. That's awesome.
You're too shy. We're trying to understand at what level one programs these factors.
Yeah. Yeah, so this is in fact, this is a C++ snippet, I guess, right? I never remember whether I put MATLAB or Python on these, but I think this is C++. Yeah.
Looks like it.
Yeah, so what's happening here is, so this is a little, this is called a post-SLAM example, which is used by actually lots of companies as well, because if you have these lasers, it's a lot of information, but you can run an algorithm to relate the location of one laser scan to the location of the next laser scan. So that gives you a binary factor between, say, x1 and x2. Maybe this one is GPS, where you start, and then you have a binary scan, and then this red one is a loop closure. Say, you've gone around the block, and you see, oh, I'm in the same place. So now you add a loop closure between your current state and the state from before. And so the way this works is you create a graph, and then you create a noise model for your measurements as well, and then you add these factors. And here they're called between factors. So you add 1, 2, 3, 4, and then a fifth, which is the loop closure. So you 1, 2, 3, 4, and then the loop closure. And then at the end, you now have a graph, and you say, you call an optimizer, and there's several optimizers implemented. You optimize using that graph, and it gives you sort of the most probable answer for the location of the robots over time.
That's what I'm trying to understand a little better. So the factors, when they say pose to or whatever, what are these intuitively? Are these stochastic? Obviously, you tried to simplify. You showed us kind of the analogy with linear equations, but these are not just linear scaling factors. These are...
No, x1 would be, for example, if it's a pose 2, we call that a 2D pose. That's an x position, a y position, and the heading of the vehicle, right? And pose 3 would be the XYZ position and the 3D orientation of the vehicle. Yeah. And so it's a multivariate optimization problem that you're trying to solve here.
So our community have been working a lot on developing tooling for normal developer, like debugging, refactoring, and designing new languages. So in this domain, do you think that we can do something for that to improve developer experience, make them more productive?
Yes. In fact, one of my students went on an internship to Holomatic in Beijing, and he did some things, but the thing that they really like him for is he created a JavaScript sort of visualizer of the factor graph as it was evolving over time. And that allowed the engineers to sort of look at different factors, looked at when the factor became high error, so maybe there was a mistake in the measurement, data association or something. And that's been a very valuable tool to work with. So yeah, I think that is very, very difficult. Whenever we do user interfaces, we hit this brick wall of it's just so hard to create with students or even engineers how to make nice interfaces for all this stuff. Students don't want to do it. There are robotics students, and people in companies don't want to do it because they just want to download the library and profit from it. And so yes, if anybody wants to create tooling for sensor fusion, etc., I'm all for it. It's a big need.
So a somehow related question. First of all, great talk, very exciting stuff and really cool. Pity about if you ask me about the ML to C++ transition. And
I don't understand why the world is not fully operating in ML.
I don't understand also why the world does not operate the way I want it, really. But a related question on a more serious side, are there any verification problems and issues that you see in this domain? Because naively, perhaps, I would expect that doing it in a language like ML, you would have a slightly easier way of doing this. But perhaps there are no issues that you would like to verify here.
No, I think in the code generation especially. So I would love to write or work with somebody to write a code generation. So typically, GT70 is a very general library. You can do anything. You can do anything from Sudokus to structure from motion to SLAM. So that also comes with a cost. It comes with a performance cost and sort of an unpredictable runtime cost. So what you would like to do is sort of describe your problem in some small language. Say, I'm going to have at most 20 of these poses. I'm going to have at most 100 3D points. and I want to do this within, say, 10 milliseconds, right? Every iteration it has to be within 10 milliseconds. And I don't want it to crash, and I don't want it to malloc more than so much. So those to me are sort of verification questions in a way, right? So I would like to be able to generate code that verifiably hits all of these basically constraints from actual practitioners. And I think there's not only interesting research to be had, but also money to be made. Yeah.
My question is sort of similar to the one that was 2 questions ago. I've done a bit of robotics, and I've used ROS, which for people who don't know is Robot Operating System, and it's sort of a higher level framework that you can use to like integrate various packages and do stuff like sensor fusion. So my question is specifically like ROS is very difficult to use in terms of like it takes a long time to learn and it's kind of clunky. So I'm wondering, do you see like opportunities for people to write new programming languages that are not just like a framework but actually replace this? And would that be something that is potentially useful to the field of robotics?
Yeah, absolutely. And I completely agree with your assessment on ROS, by the way. So especially ROS 1.0 is, so they're building ROS 2.0. To their credit, they even say it will compile on my Mac, which was a big issue with ROS 1.0. But it's clunky and people are trying, right? So Amazon is trying to create some framework for robotics, and I think NVIDIA is trying to do some framework for robotics, and Microsoft tried it in the past. And absolutely, you can try to create a language, but in the end, it's hard to see what makes a language go from something interesting that one PhD student did and then moved on to Facebook or Google or whatever, and never looked back, to something that has real adoption. And I think that's why we can't control the world in a bit. It's the same story as C++ and ML. It's like, yeah, you can wish that you can do this verifiable stuff in ML, etc., but people don't want to hear it sometimes. And I think ROS 2.0 is probably the best chance we have at sort of influencing them to do a better job in the second iteration. But if, look, I mentioned Swift. I think Swift, has some compromises because it was created where it was created, and they had to sort of be backward compatible with their universe. But it adopted a lot of features from languages that were very useful. Okay, and so I think you guys have a shining beacon sort of responsibility or opportunity in the sense of show what kind of features can be really, really useful and hope that they get adopted in sort of mainstream things. I think that's one way in which you can have a really large impact on the world.
Okay, thank you.
First of all, it's a very nice talk. It's very interesting, exciting. I also have a question related to your language. I think one of the reasons that the robotics people love C++ is performance and also limited hardware resource. A typical target processor in our community is like a Xeon, dual processors with lots of threads and multi-cores and blah blah blah, and a few gigabytes of memory. But I was wondering, what is a typical target processor hardware in the robotics world or drone? You showed us.
I don't know the answer to that sort of very well. Okay, so there's these processors, Qualcomm processors, and there's ARM cores that you want to target, etc. Especially if you want to do embedded stuff. But I'm also a little bit puzzled and a little bit sort of look. I don't want my students to think about performance. Okay, I want you guys to think about performance. All right, build those compilers that run fast. Okay, because C++ is just terrible. Is like, the reason why we build an entire Python wrapper is because we don't want to live with the compile cycle. Okay, especially if GSM uses templates, up and down, and compile times that become very, very long. So I'm trying to push all my students to be, even though I don't love Python as a language, to be at the Python level, so at least they get research done. But I wish there were like ultra fast compilers that gave ultra fast code. So over to you. On any platform.
Thanks for the great talk. So I'm curious about this drone use scenario, the follow me scenario. So can you tell us a little bit more about the computation model? Specifically, how much of the computation about vector graph computation happens on the ground station side, biker side, and how much is actually happening on the drone? And
that's an easy question to answer.
Okay.
All the computation happens on the drone.
Okay, well, so I guess the second question is probably easier than how much is the battery life?
That's an excellent question, by the way. So it turns out that if you have 4 rotors, the computer is basically like a 5th rotor in terms of energy consumption. And there's a scaling law that the smaller the drone, the smaller your battery life. The bigger the drone, the more battery you can carry, and the longer you can fly. And so the scaling works out nicely for bigger drones. But of course, we want a drone that you can just put in a backpack. So the first drone was something like 11 minutes, okay, which is not a lot. But frankly, you are not going to post 11 minutes of you biking on Facebook, which is really what this drone is for. It's like posting on social media, right? The second one is they optimized the hell out of it, and there's only six cameras now for navigation. So it has a battery life of about 23 minutes. So it's better, but it's not a whole lot, right? So it's not that you can climb, a rock for 2 hours and have the drone next to you for 2 hours. That's we're not there.
Thank you. Exciting stuff.
I have a.
So I have this guy doing a box, and it automatically recharges itself.
Yes. So Skydio is now that just came out last week. There is a box and there is a Skydio drone inside. So Skydio is sort of branching out to industrial applications as well. Imagine, say, a construction site where you want to do regular surveys. Okay. So, because believe it or not, on construction sites, people lose stuff all the time. Some of it gets stolen, some of it is just misplaced. And if you misplace a beam, of steel, that could be an expensive thing, right? So you do these occasional surveys, like say 1 a day. So now there is a little box that you can put. The Skydio drone is in there. It charges. It automatically flies out once a day, comes back, and then lands. Recharges, and so that's something that sort of enables hands-off operation over long periods of time. So that's something new and exciting.
So there was one question I was absolutely certain someone would ask, and nobody asked it, which shows how much I know about the community. I'd like more detail about your differentiable language. You said what you'd love to have is a language that has differentiable functions as first-class objects. Is this just a restriction on what computations can be done? I don't know anything about differentiable functions, like what the backpropagation or any of that. So is that a restriction? Can it be done with a type system? Is it something like ownership or something like something that will limit what computations are possible? Or how do you envision that? Because I really have no clue.
Yeah, so a differentiable function is simply a function so there's sort of, you have to calculate derivatives all the time to optimize in continuous spaces. And so there's sort of 3 ways you can do it. You can look at your function and do a symbolic, do it on pen and paper and get the derivatives. Or you can do something called numerical differentiation, which is just give our input arguments that are a little bit up, a little bit down, and then take the outputs change, and that's an approximation of the derivative. And then finally, there is this thing called automatic differentiation, which really implements, and this only works at a particular value where you want to evaluate both the function value and the derivative, where you basically use the chain rule on your expression tree, and you can do this in a forward way or in a backward way, to calculate the derivatives of a multivariate function based on all its inputs that you're interested in. And that's something called AD, and in fact, there is a whole community that looked at taking in, say, a C program and automatically creating the program that does the derivatives. We've done that in GTSAM by creating a little DSL in the C++ template language, so that at compile time, we create a tape on which we do all the automatic differentiation. It's ugly, and the code is the ugliest code I've ever written. It's like 6 months after writing it, I couldn't understand it anymore. It's that meta. But it is incredibly efficient, though. That's nice, because we do only one malloc in which we lay out the entire tape. So the fact that you do that at compile time is quite interesting. But it was a pain to create it. So if what the Google people transpires, which is build this into Swift, right? And their motivation is not sensor fusion, but deep learning, right? Deep learning is all about differentiable programming. If we can sort of ride that gravy train and have differentiable functions like right into the language, that would be amazing, right?
Yeah, so there are every year talks at PL conferences, especially with deep learning about automatic differentiation. But I was thinking that you're saying this could be a first-class language construct, constraining functions, but it seems it could be any function. It's just the compilation that you want built into the language. It's not a property of the function whether it's differentiable. It's take any function and then say, now do differentiation, either symbolic or AD or anything on it, and you want that optimization, the optimized code, to be part of the compiler, right?
Well, in Swift, you sort of, not any function will work, right? So you have to annotate and say, okay, make this one differentiable, and if this one takes inputs which are all differentiable, then you're automatically differentiable. So it builds in this protocol situation that allows you to annotate, this is going to be differentiable in that argument, but not differentiable in this argument. So there's that type of sort of annotation is going to be built in. So, thank you.
Thank you very much for the great talk. I just have a question that's not very much related to programming languages, so I'm sorry.
No, please.
I just want to ask, moving from mobile robots to manipulators, what was the main challenge that you had to face, and how did you get to work with kinematic chains that had like nonlinear forwarding of kinematics, and you have to consider all that, and then how it compares to other like common trajectory optimization methods for
yeah, actually, the challenge was not. So the challenge was sort of learning about robot dynamics and kinematics. But in fact, the reason why we started all this is because I was teaching a robotics course on mobile manipulation, and when we got to the chapter on dynamics, it was incomprehensible, and I sort of felt there has to be a better way, and so. I'm now in evangelizing mode about factor graphs, so I said, well, let's see what it looks like as a factor graph, and this is the result of a 6-link arm. This is the dynamics of that 6-link arm. And these graphs are, even if you smear them over time to do kinodynamic motion planning, this is like maybe 50 variables, and then if you do it over time, that's 5,000 variables. Still quite small. Compared to the things that we do in SLAM and structure from motion, these graphs are tiny. So in a way, this is sort of easier than working with large, mapping problems. So yeah, it became a very interesting and very straightforward application of all the things we knew.
Mapping at the same time, or don't consider that? So you have an arm, you don't know the environment around it, which is very common in flexible manufacturing, or like not common, I mean, it's not applied yet, but I guess if you think into the future for flexible manufacturing where humans are always around, like stuff is happening in the manufacturing facility, so you want to be mapping around the robot manipulator at the same time.
Yeah, we want to map around the manipulator. We want to figure out, we can use the kinematics to do better maps. We can think, each one of you is a kinematic chain, okay? So we can look at you as a kinematic chain and try to infer what joint angles you're currently exhibiting, and where the future of these joint angles is, so we can work with people. Yeah, so all of these things, now it's so nice that now the same language can be used to do both the planning and the mapping around the robots. So yeah, I'm super excited about the confluence of these two worlds, which have sort of been separate most of the time. Thank you.
And since it seems we've concluded our questioning, thank you very, very much, Frank, for an excellent talk.
Yeah, thank you.